A burger, fries, and a drink form a specific, defined set. Scale that constraint up to industrial manufacturing. A sports car factory produces a high-performance engine that must pair with a specific tire designed for high speeds. If you mix an off-road tire onto a track car, the system fails. Translating this constraint into code without a pattern creates hard-coded dependency lines. These rigid links work initially, but crack under pressure as the system grows. Introducing an off-road variant forces you to crack open existing code to add conditionals. Every new variant forces you to modify tested code rather than extending it. This creates a recurring maintenance cost and violates the open-closed principle. Manual updates for product variants distribute the logic of compatibility across the entire application. Without a centralized way to manage these relationships, the system becomes a collection of special cases that are expensive to maintain and difficult to test. The disciplined way to manage these related sets of objects is a creational pattern called the abstract factory. This pattern provides an interface for creating families of related or dependent objects without specifying their concrete classes. Strip away the academic jargon, and it is a factory of factories. Structurally, we establish abstract products. These act as the foundational contracts, dictating the rules that underlying concrete products must follow. Above them, an abstract factory interface oversees multiple concrete factories. Each concrete factory is responsible for producing its own matching family of products. By separating the stable interfaces from the varying implementations, we create a single architectural seam. This layer of abstraction allows the system to support new families of products by adding new classes rather than rewriting existing ones. To see how this architecture behaves in memory, we can map the car manufacturing constraint directly onto these software roles. The physical components, the actual sports engine and sports tire, serve as the concrete products. The assembly line dedicated to those specific parts, the sports car factory, functions as the concrete factory. The generic blueprints that define what an engine or a factory must do act as our abstract products and our abstract factory. Mapping the problem to a factory floor replaces abstract terminology with the literal logic of an assembly line. The classes become blueprints for ensuring the right parts reach the right machine. When the software reflects these physical manufacturing constraints, the organization of the code follows the logic of the business requirement. Let's build this from the ground up. The goal is to ensure that each layer only interacts with the abstraction directly above it. Step 1. The abstract products. We define interfaces for engine and tire. These are the foundational contracts for the entire system. Client code will eventually depend solely on these interfaces, remaining isolated from the hardware classes underneath. Step 2. The concrete products. We implement a sports engine and an off-road tire. These are the interchangeable implementations. Because they honor the abstract contract, you can add an entirely new family of electric car parts here later without editing the calling code. Step 3. The abstract factory. We write a car parts factory interface that specifies how to create an engine and a tire. Step 4. The concrete factories. A sports car factory implements the interface and specifically returns a sports engine and a sports tire, locking in that matched set. This bottom-up construction creates a perfectly isolated ecosystem. The logic determining how to create related objects is entirely decoupled from the business logic that uses them. Step 5. The client wiring. We instantiate our sports car factory and call its creation methods. The client code only references the engine, tire, and car parts factory interfaces. It is unaware of which concrete classes are executing at runtime. To switch families, we change one line of code to initialize an off-road car factory instead. Every subsequent line of logic remains the same. When we view all 5 steps together, we can see how the architecture enforces compatibility. The client relies entirely on the abstract layer. The execution logic bypasses the concrete implementations. This structure guarantees that objects from the same family are used together while maintaining a strict open-close architecture that scales as the product catalog grows. Real engineering requires evaluating the costs of this isolation. Abstract factory ensures families are used together, makes swapping entire product lines trivial, and isolates concrete classes from the client. However, the abstract layer is rigid. If you add a new product type, like a steering wheel, you must modify the abstract factory interface and every existing concrete factory. This creates a significant amount of boilerplate. This cost is justified when managing UI themes like Mac and Windows, handling database connection families like MySQL and MySQL Statement, or generating matched hardware sets. In a systems design interview, simply knowing the structure is not enough. You have to identify when the complexity of the pattern is worth the flexibility it provides. A common confusion is the difference between abstract factory and the factory method. Factory method generates a single product, while abstract factory generates an entire interdependent family of products. Mature design is not about applying every pattern. It is about recognizing where the requirement for matched components warrants a structured creational layer. Abstract factory is a factory of factories. It is a runtime object that produces a whole family of related products that belong together. Use this reference to cement the structure. The seam between abstraction and implementation is what gives this pattern its utility. Look at your current projects. If you find yourself manually checking the compatibility of related objects, you may have found a candidate for an abstract factory. Identifying these structural families allows you to build systems that scale through extension, keeping the core logic stable even as the product catalog expands.